Imagine that you are floating alone in deep space. There is no planet beneath you, no spacecraft nearby, no familiar sun filling half the sky with light. Only distant stars scattered across a darkness so vast that your mind cannot measure it. Then, without warning, the pressure inside your spacesuit begins to fall. The air around your body escapes into the vacuum. The gentle sound of your own breathing disappears. There is no wind against your face, no rushing noise, and no cold air pouring through the opening. There is only silence. You already think you know what happens next. You have seen it in movies. The exposed skin freezes instantly. Ice races across the visor. The body becomes rigid within seconds, transformed into a frozen figure drifting through the night. After all, deep space is unimaginably cold. Far from the warmth of stars, the surrounding universe rests only a few degrees above absolute zero. Surely, nothing warm could survive there for more than a moment. But the truth is much stranger. You would not freeze instantly. For several precious moments, your body would remain almost as warm as it was before the suit failed. Your skin would not suddenly turn to ice. Your blood would not freeze inside your veins. The warmth stored within your muscles, organs, and bones would still be there. Deep space is cold, but there is almost nothing in it capable of touching you. No cold air surrounds your body. No water carries your warmth away. No wind strips heat from your skin. The space between the stars is so empty that the ordinary meaning of cold begins to break down. On Earth, cold is something you can feel pressing against you. It moves through your clothes, across your skin, and into your body. It is carried by air, rain, snow, ice, and wind. In deep space, those things do not exist. Your body can lose heat, but only slowly, by releasing invisible infrared light into the darkness. Photon by photon, the warmth inside you begins a silent journey away from your skin. But that process takes time. Long before your body could freeze, the loss of pressure and oxygen would become the immediate danger. Consciousness would fade quickly, while the warmth inside you remained almost unchanged. You would be dying in one of the coldest environments in the universe, and yet, strangely, you would still be warm. This is the first great paradox of deep space. The cold is real, but it does not behave like winter on Earth. It does not rush toward you like an icy wind. It does not immediately seize every warm object and turn it solid. It waits. It works slowly, silently, and with almost perfect patience. And that is why the cold of deep space is far worse than most people imagine. The true danger is not that space will freeze you in a single dramatic moment. It is that everything keeping you warm, every heater, every battery, every wire, every pump, and every living system must continue working inside an environment that offers no help at all. A spacecraft traveling between the stars is not simply moving through cold. It is carrying a tiny island of warmth into an endless night. Inside its walls, air must remain warm enough to breathe. Water must remain liquid. Fuel must continue flowing. Batteries must stay alive. Computers must operate inside narrow temperature limits. Outside those walls, there is almost nothing. No atmosphere to distribute heat, no nearby ocean to store it, no warm ground beneath the ship. And eventually, perhaps no bright sun close enough to replace the energy being lost. Every degree of warmth must come from somewhere. Every watt must be protected. Every invisible thread of heat must be guided through the spacecraft with extraordinary precision. Because in deep space, warmth is not part of the environment. It is something you must bring with you. And before we can understand how easily that warmth can disappear, we first need to understand something far more fundamental. How does heat move through a place where there is almost nothing for it to move through? Heat is always moving. Even now, as you sit or lie somewhere on Earth, warmth is leaving your body. Some of it passes into the chair beneath you. Some drifts into the air around your skin. Some escapes as invisible light, traveling outward in every direction. You do not notice most of it because the exchange is constant. The room warms you. You warm the room. The blanket above you slows the process. The mattress beneath you absorbs a little energy. Air brushes against your face, carries warmth away, and replaces it with cooler air. This quiet movement of heat is so ordinary that we rarely think about it. But nearly every way you have ever experienced cold depends on matter being present. Heat can move in three basic ways. The first is conduction. Conduction happens when two materials touch. Place your hand against a cold window on a winter morning, and heat begins moving from your warm skin into the cooler glass. Nothing visible flows between them. The atoms in your hand simply collide with atoms in the window, passing tiny amounts of energy from one particle to the next. This is why metal often feels colder than wood, even when both have been sitting in the same room. The metal is not necessarily at a lower temperature. It is simply better at conducting heat away from your skin. Your body interprets that rapid loss of energy as cold. The second way heat moves is convection. Convection requires a fluid, which means either a liquid or a gas. Think of a cold wind crossing your face. The air touching your skin warms slightly, but before it can remain there, the wind carries it away. Fresh, cold air immediately takes its place, absorbs more heat, and is swept away as well. This cycle repeats thousands of times. The faster the wind moves, the faster your body loses heat. That is why a calm winter day and a windy winter day can feel completely different, even when the thermometer shows the same temperature. Water is even more effective. Step into a cold lake, and the water surrounding your body absorbs heat much faster than air. Each moving layer of water carries away energy and replaces it with colder water from nearby. This is why cold water can become dangerous so quickly. Your body is not merely surrounded by low temperature. It is surrounded by matter that is actively carrying your warmth away. Then there is the third method, radiation. Every object warmer than absolute zero releases energy as electromagnetic radiation. A campfire radiates visible light and infrared energy. The sun radiates across an enormous range of wavelengths. Your own body also glows, though not in a way your eyes can see. At human temperature, most of that glow lies in the infrared part of the spectrum. With the right camera, a person standing in darkness appears bright and warm. Their face, hands, and clothing outlined by the heat they are constantly emitting. Unlike conduction and convection, radiation does not need air. It does not need water. It does not need any material between one object and another. Radiation can cross a vacuum. In fact, nearly every bit of sunlight reaching Earth has traveled through about 93 million miles of almost empty space before touching the atmosphere, the ocean, the ground, or your skin. This is the key to understanding why you would not instantly freeze in deep space. Conduction requires contact. Convection requires surrounding matter. But in the vacuum between planets, there is almost nothing touching you. There are particles in space, but they are spread so thinly that they cannot remove heat the way air or water can. A few atoms may strike your body from time to time, but compared with the unimaginable number of molecules surrounding you on Earth, their effect is almost meaningless. There is no cold wind. There is no icy water. There is no atmosphere pressing against every part of your skin. So the two fastest ways your body normally loses heat are almost completely gone. Only radiation remains. Your body continues emitting infrared light into the darkness, but it contains a great deal of stored thermal energy. Your blood, muscles, organs, bones, and skin all hold warmth. Losing that energy through radiation alone is not immediate. Imagine taking a hot drink outside on a cold day. If the wind is strong, it cools rapidly. If you pour it into cold water, it cools even faster. But place the same drink inside a well-insulated vacuum bottle and it may remain warm for hours. A spacecraft uses the same principle. So does a spacesuit. The vacuum that makes space dangerous in so many other ways can also act as an excellent insulator. This creates a strange situation. A human exposed to vacuum would face catastrophic problems almost immediately, but rapid freezing would not be one of them. Without pressure, air would rush from the lungs. Oxygen in the bloodstream would no longer be replaced. Consciousness would fade in a matter of seconds. Moisture on the tongue and in the airways could begin to boil, not because it had become hot, but because the pressure around it had fallen so low. At low pressure, liquids can boil at much lower temperatures. That boiling moisture would produce some local cooling, especially around the mouth and respiratory surfaces. But deep within the body, the core temperature would remain close to normal for much longer. The person would lose consciousness while still warm. It is an unsettling thought. The coldest-looking environment imaginable would not kill through cold first. The vacuum would take away pressure, then oxygen. Only later would the remaining warmth slowly radiate into the darkness. This tells us something important. Cold is not simply a low number on a thermometer. What matters is how quickly heat can move. A block of metal and a piece of wood can share the same temperature but feel very different. Cold air and cold water can share the same temperature but affect the body at radically different speeds. And a nearly empty vacuum can be associated with temperatures close to absolute zero while cooling a warm object surprisingly slowly. Deep space does not surround you with cold matter. It surrounds you with almost no matter at all. The cold cannot reach out and touch you the way winter air can. Instead, you must slowly give your warmth away, one invisible photon at a time. And this leads to a deeper question. When scientists say that deep space is only a few degrees above absolute zero, what exactly are they measuring? How can emptiness have a temperature? And if space itself is so cold, how can a spacecraft in that emptiness become hot enough to destroy its own electronics? When you hear that deep space is only a few degrees above absolute zero, the number sounds final. It sounds like a place where all warmth must vanish, a place colder than Antarctica, colder than liquid nitrogen, colder than any winter your body could survive. But there is a problem with that picture. Temperature is not something emptiness simply possesses in the same way air, water, or metal does. Temperature describes the motion of matter. In a warm gas, atoms and molecules move rapidly, colliding with one another at high speed. In a colder gas, they move more slowly. Cool the material enough, and the motion becomes smaller and smaller, approaching the theoretical limit known as absolute zero. But a perfect vacuum contains almost no atoms or molecules to measure. There is no dense collection of particles vibrating together. No surrounding substance pressing against a thermometer. So asking for the temperature of empty space is not quite the same as asking for the temperature of a room. It is closer to asking what temperature an object would eventually reach if it were left alone there for a very long time. And the answer depends on everything that object can see. A spacecraft in deep space is surrounded not by cold air but by radiation. Photons arrive from stars. They arrive from planets. They arrive from clouds of dust warmed by distant suns. They arrive from the spacecraft's own instruments, engines, batteries, and living passengers. And beneath all of these brighter sources lies a faint glow that fills the entire observable universe. The cosmic microwave background. This radiation is ancient. It began its journey when the universe was only a small fraction of its current age, long before stars, planets, or galaxies existed in their familiar forms. As the universe expanded, the radiation stretched with it. Its wavelengths became longer, its energy fell. Today, it surrounds us from every direction as a nearly uniform microwave glow corresponding to a temperature of about 2.7 Kelvin. That is roughly 455 degrees below zero on the Fahrenheit scale, only a few degrees above absolute zero. But this does not mean that a wall of 2.7 Kelvin cold is pressing against every object in space. The cosmic background is extraordinarily faint. It does not remove heat the way icy water does. It does not flow across a surface like wind. It simply provides the dimmest possible bath of radiation against which warmer objects slowly release their own energy. A warm object emits more infrared radiation than it receives. So it cools. As it becomes colder, the amount of radiation it emits decreases. Cooling slows. Eventually, if no other source of energy is present, the object approaches a point where it radiates away exactly as much energy as it absorbs from its surroundings. That is thermal equilibrium. The temperature it reaches is determined not by emptiness alone, but by the balance between incoming and outgoing energy. This distinction changes everything. Deep space does not impose a single temperature on every object. It offers an energy environment. A dark rock far from any star may slowly cool toward the background temperature. A powered spacecraft in the same region may remain warm for decades. A human habitat might hold its interior near room temperature while its outer surfaces become bitterly cold. A radioisotope generator can glow with heat even in interstellar darkness because its energy comes from within. And an object near the sun can become dangerously hot despite floating in a vacuum whose background radiation is only a few degrees above absolute zero. The important question is never simply, how cold is space? The better question is, how much energy is arriving and how much energy is leaving? Imagine a small black plate floating near Earth's orbit. Turn one side toward the sun and sunlight pours onto it. Each square meter receives more than 1,000 watts of radiant energy. The plate absorbs some of those photons. Its atoms vibrate more strongly. Its temperature rises. As it grows warmer, it emits more infrared radiation into space. Eventually, if its orientation remains fixed, it reaches a temperature where the energy it emits matches the energy it absorbs. Now rotate the plate so that it faces away from the sun. The powerful stream of sunlight disappears. The plate continues radiating its stored warmth into the darkness, but very little energy replaces it. It begins to cool. Nothing has changed about the vacuum surrounding it. Nothing has changed about the cosmic background. Only the plate's view of the sun has changed. This is why geometry becomes climate in space. Direction matters. Color matters. Surface material matters. A shiny metallic surface may reflect much of the sunlight that strikes it. A dark surface may absorb more and grow hotter. A surface designed to radiate infrared energy efficiently can cool faster than one designed to retain heat. Two objects floating beside one another can settle at very different temperatures simply because they have different shapes, coatings, orientations, or internal power sources. Even different parts of the same spacecraft can experience completely different thermal realities. A sunlit panel may absorb intense radiation. A shadowed instrument behind it may see only cold space. A battery buried deep inside the structure may remain warm because it is surrounded by electronics. A thin antenna extending outward may cool rapidly because it has a wide view of the dark sky. There is no air to smooth out these differences. On Earth, the atmosphere constantly redistributes heat. Warm air rises, cool air sinks. Wind carries energy across cities, oceans, forests, and mountains. Clouds reflect sunlight. Water stores warmth and releases it slowly. Even during a cold night, the air around you connects every surface to every other surface through countless molecular collisions. In space, those connections disappear. Every surface exists in its own radiation landscape. It absorbs energy from whatever lies in front of it. It emits energy according to its own temperature. It exchanges heat through physical contact only where it is attached to another part of the spacecraft. The result is a universe where hot and cold are not regions you enter in the ordinary sense. They are balances you create. A spacecraft does not simply pass through a cold environment and become cold. Its temperature is continuously negotiated between sunlight, darkness, internal heat, insulation, and the ability of its surfaces to radiate energy away. And that negotiation never stops. A computer switches on and generates heat. A scientific instrument powers down and begins to cool. The spacecraft turns slightly. A radiator sees more of the sun. A shadow moves across an antenna. A battery heater activates. A crew member begins exercising and releases additional metabolic warmth into the cabin. Each event changes the thermal balance, sometimes only slightly, sometimes enough to threaten the mission. This is why the cosmic background should be understood as a floor, not a force. It is the coldest distant condition toward which an isolated object may slowly drift. But between a warm spacecraft and that floor lies a long and complicated exchange of energy. The void does not reach into the ship and pull the heat away. The ship releases that heat on its own, and whether it cools, warms, or remains stable depends on how carefully that release is controlled. This brings us to one of the strangest sights in the solar system. A single world where the same ground can be hot enough to boil water and, only a short distance away, cold enough to trap ice for billions of years. Not because the world moves between hot space and cold space, but because one place sees the sun and the other does not. Now imagine standing on the moon. Above you, the sky is completely black. There is no blue atmosphere, no drifting cloud, and no haze softening the distant horizon. The sun hangs in the darkness with a sharpness you have never seen from Earth. Its light falls directly onto the ground. There is nothing in the way. No air scatters the sunlight across the landscape. No wind carries warmth from one place to another. No weather moves through the valleys or across the plains. Every surface must face the sun alone. The ground beneath the sunlight absorbs energy for days at a time. Dust, stone, and metal slowly grow hotter as photons continue pouring down from above. But nearby, perhaps behind the wall of a crater or beneath the shadow of a boulder, the situation is completely different. There, the sun has disappeared. The ground receives almost no direct energy. It continues releasing its remaining warmth as infrared radiation, sending it upward into the black sky. There is no warm air from the surrounding landscape to replace what has been lost. No breeze crosses the boundary between light and shadow. No atmosphere mixes the two climates together, so the shadow grows colder and colder. The change can happen across only a few steps. One patch of ground may be intensely heated by sunlight, while another nearby patch remains trapped in deep cold. Both exist at the same time, on the same world, under the same sky. This would be almost impossible on Earth. Even in the harshest desert, air moves between sunlight and shade. The ground conducts heat sideways. Winds redistribute energy. The atmosphere absorbs infrared radiation and sends part of it back toward the surface. At night, stored heat escapes gradually. On the moon, the environment offers almost none of this protection. Light and shadow become separate thermal worlds. Where sunlight lands, energy accumulates. Where it does not, energy drains away. This is one of the most important truths about temperature in space. Distance alone does not determine whether something becomes hot or cold. Direction matters just as much. A surface facing a star may become dangerously hot. Turn that same surface away, and it may begin cooling toward temperatures far below anything found naturally on Earth. Nothing about the surrounding vacuum has changed. Only the view has changed. Now carry this idea away from the lunar surface and place it on a spacecraft. Imagine a small vessel traveling between Earth and the Moon. Its sunward side is constantly illuminated. Sunlight strikes the hull, the antennas, the windows, and the exposed equipment mounted outside. Each surface absorbs some portion of that energy. The opposite side of the spacecraft faces the dark. It continues radiating warmth outward, but receives little energy in return. One side begins to expand as its materials become warmer. The other side contracts as it cools. The entire spacecraft is caught between two climates. A few feet of metal may separate a hot surface from a cold one. A cable may pass from a warmed electronics compartment into a shadowed structure where its temperature falls dramatically. A fuel line may run through several different thermal zones before reaching an engine. A camera exposed to sunlight may need protection from overheating, while another instrument behind it may need a heater to prevent becoming too cold. Spacecraft are not simply hot or cold. They are thermal maps. Every panel, wire, tank, lens, battery, and bolt exists inside its own small climate. And these climates shift whenever the spacecraft moves. Turn the vehicle slightly toward the sun, and a radiator that was releasing heat into darkness may begin absorbing sunlight. Rotate an instrument into shadow, and its temperature may start falling. Deploy a large solar panel, and it can block sunlight from equipment behind it, creating a new cold region that did not exist before. Even a small change in orientation can redraw the thermal landscape of the entire vehicle. This is why some spacecraft rotate slowly during long journeys. During the Apollo missions, the spacecraft could not simply maintain one fixed side toward the sun for the entire trip to the moon. If it had, one half would have continued heating, while the other half continued cooling. Over many hours, those differences could have become dangerous. So the vehicle slowly rolled through space. The astronauts called this motion the barbecue roll. Like food turning above a fire, the spacecraft exposed each side to sunlight in sequence. No surface remained heated for too long. No surface remained in darkness for too long. The slow rotation averaged the sunlight across the vehicle and prevented the most extreme temperature differences from developing. It was a simple movement solving a complex thermal problem. But even this solution reveals how strange the space environment really is. On Earth, you rotate food above a fire because hot air rises and flames heat one side more strongly. In space, the fire is nearly 93 million miles away. The energy crosses that entire distance as radiation, reaches the spacecraft, and creates two completely different climates on opposite sides of the same machine. The spacecraft must rotate not because space is uniformly cold, but because space is thermally uneven. Sunlight is intense and directional. Darkness offers almost no energy in return. Between them is a narrow region where life and machinery can survive. This is also why the exterior of a spacecraft may look so unusual. Some surfaces are dark, others are bright white. Some are covered in reflective gold or silver blankets. Each color and material is chosen for the way it interacts with energy. A dark surface may absorb sunlight efficiently. A bright surface may reflect much of it. A specially designed radiator may release infrared heat into space while reflecting visible sunlight. A reflective insulation blanket may reduce heat exchange in both directions, keeping solar energy out while keeping internal warmth in. The appearance of a spacecraft is partly the appearance of its climate control system. Every surface is making a decision about light. Absorb it, reflect it, retain heat, or release it. Inside the hull, however, the goal is very different. The passengers cannot live inside constantly shifting climates. They need air that remains comfortable, water that stays liquid, computers that stay within safe limits, batteries that do not become too cold to function, and equipment that does not overheat when switched on. The outside of the spacecraft may experience extremes, but the interior must remain stable. That stability does not happen naturally. It must be manufactured. The spacecraft must gather heat from places where too little exists, move it away from places where too much is accumulating, and release the excess into exactly the right direction. It must build an artificial climate inside a universe that has no climate at all. And every moment that climate survives depends on a hidden network of insulation, pumps, heaters, fluid lines, and radiators working quietly behind the walls. Inside the spacecraft, the temperature feels ordinary. The air is comfortable. Water moves through narrow pipes. Small lights glow above instrument panels. Fans turn somewhere behind the walls, creating a soft mechanical hum that never completely disappears. A crew member rests inside a sleeping compartment. Another works at a computer. A third prepares food in a space no larger than a small closet. Everything appears calm, but the calm is artificial. Every breath, every circuit, every warm surface inside the cabin is adding heat to a sealed world that has no natural way to release it. A human body at rest produces roughly as much heat as a small light bulb. During exercise, that amount can rise several times higher. Now add computers, communication systems, lighting, batteries, pumps, scientific instruments, and life support equipment. Every one of them produces waste heat. On Earth, getting rid of this heat is usually easy. Warm air rises, cool air sinks. Fans move air through a room. An air conditioner transfers heat outdoors, where the atmosphere carries it away. Even opening a window allows warm indoor air to mix with cooler air outside. But a spacecraft cannot open a window. Outside the hull, there is no atmosphere waiting to absorb excess heat. There is no breeze, no surrounding ocean, no cloud of cool air. A spacecraft can be surrounded by darkness only a few degrees above absolute zero and still overheat from the energy trapped inside it. This is one of the strangest dangers of spaceflight. The vacuum is an excellent insulator. It slows the loss of warmth when a spacecraft is cold. But when the spacecraft becomes too warm, the same vacuum makes cooling difficult. There is only one final way for heat to escape: radiation. Every watt of unwanted thermal energy must eventually reach a surface exposed to space and leave as infrared light. Before that can happen, however, the heat has to travel through the spacecraft. Imagine a crew member sleeping in a small cabin. Their body warms the nearby air. Without gravity-driven convection, that warm air does not naturally rise toward the ceiling. In microgravity, warm and cool air do not separate the way they do on Earth. They remain where they are unless fans move them. The cabin's ventilation system pulls the warmed air away. It carries that air through filters, carbon dioxide removal equipment, humidity control systems, and heat exchangers. There, the excess warmth passes into a circulating fluid. That fluid may be water inside the pressurized cabin because water is safe, stable, and very effective at carrying heat. The warmed water travels through pipes hidden behind panels. It passes the heat from the crew, computers, and life support systems toward another loop connected to the outside of the station or spacecraft. Eventually, the energy reaches a radiator. A radiator in space does not look like the radiator in a house. It does not warm surrounding air. There is no surrounding air. Instead, it presents a large surface to the darkness and emits infrared radiation into the sky. The warmer the radiator becomes, the more energy it can release. Photon after photon leaves the surface and travels away from the spacecraft. Some may cross the solar system. Some may continue into interstellar space. Most will never touch another object. A tiny portion of the warmth once held inside a human body has become invisible light moving forever through the universe. This entire process is happening constantly. Heat begins in a living cell, it enters the cabin air, it moves into a heat exchanger, it crosses into coolant, it travels through pipes, it reaches a radiator, and finally it disappears into the dark. If any part of that chain fails, the heat begins to accumulate. A pump slows down. A valve becomes stuck. Coolant stops flowing through one section of the vehicle. A radiator turns slightly toward the sun. The cabin may still feel normal at first. The change can be almost invisible. But computers continue producing heat. Bodies continue producing heat. Life support systems continue running. The temperature begins to rise. Electronics become less reliable. Battery performance changes. Humidity increases as the crew sweats. Moisture condenses on cooler surfaces and forms floating droplets in microgravity. The spacecraft is still surrounded by what people call the cold of space. Yet the people inside may be slowly cooking. This is why insulation alone cannot protect a spacecraft. A perfectly insulated vehicle would hold warmth extremely well, but it would also trap every watt of waste heat inside. Sooner or later, the interior would become too hot. Engineers must therefore create a carefully controlled compromise. They need to prevent heat from escaping where it is needed, and release heat where it is dangerous. Some parts of the spacecraft are wrapped in multi-layer insulation. These thin reflective layers reduce the transfer of radiant energy. They help prevent intense sunlight from heating the interior. They also slow the loss of warmth from equipment located in shadow. Other parts are deliberately left thermally exposed. Radiators are designed to release heat efficiently. Heaters are attached to components that would otherwise become too cold. Pipes and conductive materials move warmth from one location to another. The spacecraft becomes a carefully arranged landscape of thermal pathways. Heat is guided through it almost like water moving through an irrigation system. Some channels carry energy away. Others preserve it. Some components must remain cool. Others must be protected from cold even while they are powered off. A camera detector may need to be chilled to reduce electronic noise. A nearby battery may need constant heating to retain capacity. A fuel line may require a heater to keep its propellant liquid. A computer may need a conductive connection to a radiator so it does not overheat. All of these conditions can exist only a short distance apart. A spacecraft does not have one temperature. It has hundreds, perhaps thousands. Each component lives within its own narrow range. Too warm and materials expand, lubricants thin, electronics fail, or batteries become unstable. Too cold and seals harden. Fluids freeze, metals contract, and electrical components drift outside their designed performance. The thermal control system must keep all of these small climates alive at once. It must do so while the spacecraft turns, while instruments switch on and off, while crew members sleep, work, and exercise, while sunlight changes direction, while the vehicle passes into shadow, and while the available power rises and falls. Near Earth, this challenge is difficult but manageable. The sun is bright. Solar panels generate abundant electricity. Heaters, pumps, fans, and computers can operate with relatively generous power budgets. Earth itself also reflects sunlight and radiates infrared warmth toward nearby spacecraft. Even the dark side of an orbit is not completely isolated from planetary heat. But this comfort does not last forever. As the spacecraft begins moving outward, Earth becomes smaller behind it. The sun still shines brightly at first. Then, almost imperceptibly, its power begins to fade. The light may still appear brilliant to human eyes, but the energy it carries falls with every mile. Solar panels produce less electricity. External surfaces absorb less warmth. Heaters remain switched on for longer. And the artificial climate inside the ship begins depending less on the star behind it and more on the limited energy carried on board. The crew may notice nothing. The cabin remains warm. The fans continue turning. The lights continue glowing. But beyond the window, the sun is slowly becoming smaller, and the spacecraft is beginning the long walk away from the fire. Imagine standing beside a campfire on a cold, moonless night. Close to the flames, the heat feels immediate. It reaches your face, your hands, and the front of your clothes. You can feel it even before you move near enough to touch anything warm. Now take a few steps backward. The fire still looks almost as bright, but the warmth becomes weaker. Walk farther. The flames shrink against the darkness. The light still reaches your eyes, but far less energy reaches your skin. Eventually, the fire becomes only a bright point in the distance. You can still see it, but you can no longer feel it. This is what happens to a spacecraft as it leaves the sun. Near Earth, the sun dominates almost every thermal decision. Its light powers solar panels. It warms the hull. It heats planets, moons, dust, and the thin upper atmosphere surrounding Earth. At our distance, every square meter facing the sun receives roughly 1,360 watts of solar energy before accounting for reflection and orientation. That is more than enough to heat an unprotected surface. It is also enough to generate useful electricity from relatively modest solar arrays. Near Earth, the thermal problem is often not finding warmth. It is controlling an abundance of it. Spacecraft must reflect sunlight, release waste heat, and avoid allowing their sun-facing surfaces to become too hot. But the sun's energy does not remain equally strong as you travel outward. It follows one of the simplest and most unforgiving rules in physics: the inverse square law. Double your distance from the sun, and the available solar energy does not fall by half. It falls to 1/4. Travel 3 times farther away, and only 1/9 remains. 10 times farther away, and the sunlight carries just 1/100th of the energy it delivered near Earth. The sun may still look brilliant. Human eyes are incredibly sensitive to light. But brightness and warmth are not the same thing. A distant flame can remain visible long after its heat has faded. The first major stop on our outward journey is Mars. Mars orbits about 1.5 times farther from the sun than Earth does. There, sunlight is less than half as intense. The sun still appears as a recognizable disk in the sky. The Martian day is bright enough for solar-powered rovers to operate, and solar panels can still provide meaningful electrical power. But the margin has already narrowed. Panels must be larger or more efficient. Dust can become a serious threat because even a thin layer reduces the sunlight reaching the cells beneath it. And when the sun falls below the horizon, the surface loses heat quickly. The Martian atmosphere is too thin to store much warmth. Nighttime temperatures can fall far below the freezing point of water, forcing landers and rovers to conserve power and protect their batteries and electronics until morning returns. Near Earth, sunrise is ordinary. On Mars, sunrise can be a form of rescue. As we continue outward, we cross the asteroid belt and approach Jupiter. From a distance, Jupiter is immense. Its storms are larger than Earth. Its magnetic field stretches millions of miles through space. Its moons form a miniature planetary system of their own. But the sun has changed. At Jupiter's orbit, only about 4% of the solar energy available near Earth remains. The sun is still far brighter than every other star in the sky, but its power has been reduced by more than 95%. A solar-powered spacecraft can still function there, but only with careful design and very large arrays. The sunlight that once poured generously across every square meter has become something that must be collected. Every panel matters. Every degree of orientation matters. Every shadow cast by an antenna or instrument matters. Solar power is no longer an effortless resource. it has become a limited harvest. Beyond Jupiter lies Saturn. Here, sunlight has fallen to roughly 1% of its strength near Earth. The sun is still unmistakable. It illuminates Saturn's rings, turning countless particles of ice into one of the most beautiful structures in the solar system. Yet the same light carries very little warmth to a spacecraft. A panel that produced hundreds of watts near Earth may produce only a small fraction of that amount here. Heaters must run longer. Batteries receive less power. Instruments must be designed around stricter energy budgets. The ship has moved far enough from the fire that simply seeing the flames no longer means feeling them. Then comes Uranus. The sun is now a brilliant point, rather than the commanding presence seen from the inner planets. Its energy is less than half of 1% of what Earth receives. The exterior of a spacecraft absorbs only a faint trace of solar warmth. Large solar arrays become increasingly impractical. They would need enormous surface area to collect useful power, adding mass, structural complexity, and vulnerability. The spacecraft must rely more heavily on energy carried from home. And still the journey continues. At Neptune, the sun is about 30 times farther away than it is from Earth. Its light has been reduced to roughly 1/900th of the solar energy available in our orbit. To the human eye, the sky would not be completely dark. The sun would still outshine every other star by an enormous margin. But it would look small, distant, almost delicate. It would cast shadows. It would illuminate Neptune's blue clouds and the icy surfaces of its moons. But it would offer almost no useful warmth to a small spacecraft drifting nearby. This is one of the great illusions of deep space. The sun remains visible long after it stops being thermally generous. The crew could look through a protected window and see the star that once warmed every ocean, forest, and city on Earth. It would still appear bright enough to remind them of home. But the ship would no longer feel its heat. Every comfortable degree inside the cabin would now come from energy generated on board. Beyond Neptune lies the Kuiper Belt. Here, icy objects move through orbits lasting centuries. Pluto travels through this dim region, along with countless smaller worlds left over from the formation of the solar system. The sun is no longer a disk that dominates the sky. It is a fierce point of white light surrounded by stars. Solar energy has fallen below 1 watt per square meter in the region near Pluto. That amount may still matter over a large enough area, but it is no longer the foundation upon which a deep space mission can safely depend. The old relationship between sunlight and survival begins to break. Closer to Earth, a spacecraft may use insulation to keep sunlight out. Here, insulation is used to keep every remaining watt inside. Closer to Earth, radiators may struggle to release excess heat. Here, engineers may deliberately reduce radiator exposure to prevent the spacecraft from cooling too quickly. Closer to Earth, instruments can often operate at the same time. Here, they may need to take turns. One scientific system awakens, another shuts down. Power is moved carefully from one purpose to the next. A camera warms itself before opening its protective cover. A transmitter waits until enough electrical energy is available to send data home. A heater activates around a fuel line while another component is temporarily allowed to cool. The spacecraft has entered a different thermal economy. Warmth is no longer something abundant that must be removed. It is something scarce that must be rationed. Now imagine continuing beyond the Kuiper Belt. The familiar planets remain behind. The sun becomes one star among many, distinguished mostly because the spacecraft remembers where it came from. There is no sharp boundary where solar warmth suddenly ends. It simply fades, mile after mile, year after year. The decline is smooth, mathematical, and impossible to negotiate with. At sufficiently great distances, sunlight contributes almost nothing to the ship's energy budget. Solar panels become dark wings with little purpose. The outside surfaces cool toward the radiation environment of interstellar space. Only the spacecraft's internal systems remain warm. A computer processor generates a small amount of heat. A transmitter warms when it sends a signal. Electrical current passes through a heater strip. A radioactive atom decays somewhere inside a protected generator, releasing energy that may help keep a critical instrument alive. This is the moment when the spacecraft truly becomes an isolated world. It can no longer depend on the star behind it. It must carry its own fire. That fire cannot be ordinary combustion. There is no endless supply of fuel and oxygen. It cannot depend on solar panels, because the light has become too weak. It must come from something slower, something that can produce heat continuously for decades without moving parts, without refueling, and without any help from the environment outside. Deep space probes carry such a fire. It is hidden inside dense protective material. It does not flicker. It does not burn in the ordinary sense. It comes from unstable atoms, quietly transforming into other atoms, releasing a small and steady flow of heat as they change. That heat becomes electricity, and the heat that cannot become electricity is not wasted. Far from the sun, it may be the only thing preventing the spacecraft from freezing. Beyond the last useful sunlight, every functioning circuit, every liquid fuel line, and every signal sent toward Earth depends on this shrinking reserve of energy. Because once the sun has faded into the distance, every watt becomes life. Far beyond the orbit of Neptune, the sun still shines, but it no longer warms the spacecraft in any meaningful way. Its light crosses billions of miles before reaching the hull, spreading thinner with every mile. Solar panels that once could have powered instruments, heaters, and computers now receive only a faint trace of their former energy. The spacecraft has crossed an invisible threshold. It is no longer living on sunlight. It is living on what it carried from home. Hidden inside the vehicle is a small source of continuous heat. There is no flame, no smoke, no moving piston. Only a collection of unstable atoms slowly changing into something else. With each decay, a tiny amount of energy is released. One event is almost nothing, but billions upon billions of them, happening continuously inside a carefully constructed generator, create a steady flow of warmth that can last for decades. The material used for many deep space missions is plutonium-238. It is not used like the fuel inside a nuclear reactor. There is no controlled chain reaction and no possibility of the generator becoming a nuclear explosion. The atoms simply decay naturally. They would release their heat whether they were placed aboard a spacecraft, stored on Earth, or buried beneath the surface of another world. Engineers take advantage of that quiet, predictable process. The heat is collected. Part of it is converted into electricity. The rest spreads into the spacecraft or radiates away from the generator's outer fins. Near Earth, such waste heat might be considered an inconvenience. Far from the sun, it is a gift. It can be guided into the spacecraft's structure. It can help keep fuel lines from freezing. It can protect batteries, computers, scientific instruments, and mechanical systems from the surrounding cold. The generator becomes two things at once: a power station and a furnace. This is how some of humanity's most distant machines have survived. Voyager 1 and Voyager 2 left Earth in 1977. Their original mission was to explore the giant planets, worlds so far away that sunlight was already becoming a limited resource. Voyager 1 passed Jupiter and Saturn. Voyager 2 continued past Uranus and Neptune, completing the only close exploration of those distant planets ever attempted. Then both spacecraft continued outward. They did not stop after their planetary encounters. Gravity had given them enough speed to escape the sun's planetary neighborhood and travel toward interstellar space. The worlds they visited gradually fell behind. Jupiter became a point. Saturn disappeared into the brightness surrounding the distant sun. The familiar arrangement of the solar system slowly collapsed into a single direction in the sky. Ahead lay no destination the spacecraft could reach within a human lifetime, only the long darkness between stars. Each Voyager carried 3 radioisotope thermoelectric generators. At launch, those generators provided enough electricity to operate a collection of scientific instruments, computers, heaters, communication equipment, and attitude control systems. But radioactive power does not remain constant forever. The plutonium slowly decays. The devices that convert its heat into electricity also become less efficient with age. Year after year, the available electrical power declines, not suddenly, not enough to create an obvious crisis from one day to the next. The change is closer to watching the level of a candle fall. Almost nothing seems different when you look for a few seconds, but return after many hours and the candle is shorter. For Voyager, the decline has continued for decades. A few watts disappear each year. That may sound insignificant. A few watts would barely matter in a house on Earth. It might represent a small lamp, a phone charger, or a fraction of the power used by an ordinary appliance. But aboard a spacecraft operating at the edge of survival, a few watts can decide whether an instrument remains awake. It can decide whether a heater continues protecting a fuel line. It can decide whether a computer stays above its minimum operating temperature. It can decide whether the spacecraft has enough power to turn itself, aim its antenna, and send one more faint signal toward Earth. The engineers responsible for Voyager cannot replace the generators. They cannot add a larger battery. They cannot send a repair vehicle carrying new fuel. The spacecraft are so distant that even radio commands take many hours to cross the space between Earth and the probes. There is only one strategy: use less. Over the years, systems have been shut down one by one. Some scientific instruments completed their work and were turned off permanently. Heaters were disabled where engineers believed a component might survive without them. Non-essential systems were sacrificed to preserve the spacecraft's most important functions. It is a careful form of retreat, not from distance, but from complexity. The spacecraft began their journeys as fully illuminated houses, every room active and every instrument listening. As power declined, one room after another became dark. A heater stopped drawing current. An instrument fell silent. A backup system was no longer kept ready. The remaining electricity was moved toward the systems that mattered most. The computers that receive commands, the thrusters that maintain orientation, the transmitter that sends data home, and the large dish antenna that must remain pointed toward a planet now hidden near a distant star. Some components continued operating even after their heaters were switched off. They cooled below the temperatures their designers had originally considered safe. And yet they survived. Perhaps the original limits contained generous engineering margins. Perhaps the materials were more tolerant than expected. Perhaps the slow and stable cooling of deep space was less damaging than repeated temperature swings. Or perhaps some systems were simply fortunate. In engineering documents, a component has a defined operating range. In reality, there is sometimes a narrow region beyond that range where it may continue working. But no one knows exactly where the true boundary lies until it is crossed. Voyager has spent years traveling close to those unknown boundaries. Each newly disabled heater becomes an experiment no one originally planned. A component grows colder. Engineers watch the telemetry. If the signal remains stable, the mission continues. If a voltage changes or an instrument begins behaving strangely, they must decide whether to restore power, change the operating schedule, or accept that another system has reached the end of its life. The spacecraft cannot tell them that it feels cold. It can only report numbers, temperatures, voltages, currents, Signal strength. The quiet language of a machine slowly losing energy in interstellar darkness. This creates a strange relationship between power and survival. Operating an instrument produces heat. That heat can help keep nearby components warm. But operating the instrument also consumes electricity. Turning it off saves power, yet removes one of the heat sources inside the spacecraft. The decision to conserve energy can therefore make the spacecraft colder. As it grows colder, additional heaters may be needed. Those heaters consume more of the electricity that engineers were trying to save. This is the thermal puzzle of deep space. Power becomes heat. Heat preserves the systems that generate and control power. Each depends on the other. As long as the balance holds, the spacecraft remains alive. But the margin becomes thinner each year. Voyager's eventual end will probably not look dramatic. There may be no explosion, no collision with a planet, no final image showing the spacecraft frozen beneath a distant sky. Instead, a critical system may simply become too cold or too weak to continue. Perhaps a thruster will no longer respond reliably. Perhaps the spacecraft will lose the ability to keep its antenna aimed at Earth. Perhaps a computer will stop processing commands, or the transmitter may finally lack enough power to send a detectable signal across the expanding distance. From Earth, the end may arrive as silence. One day, a station will listen. The expected signal will not appear. Engineers may send another command and wait through the long round trip. They may adjust antennas, search nearby frequencies, and listen again. But the spacecraft will remain quiet. Far away, it may still contain a little warmth. The plutonium will continue decaying. Atoms will continue releasing energy. But the carefully maintained connection between heat, electricity, orientation, computation, and communication will have broken. The machine may still exist. It will simply no longer be a functioning spacecraft. It will become an artifact drifting between stars, a small object from Earth carrying a silent record of the world that built it. This is why every watt becomes life in deep space. Electricity is not merely what turns on an instrument. It keeps fuel liquid. It keeps seals flexible. It allows computers to awaken. It moves heat from one part of the spacecraft to another. It maintains the orientation that lets radiators cool and antennas communicate. Near Earth, power allows a spacecraft to perform its mission. Far from the Sun, power allows the spacecraft to remain a spacecraft at all. A robotic probe can survive this decline by becoming simpler. It can surrender instruments. It can stop collecting certain kinds of data. It can allow non-essential components to freeze. It can gradually reduce itself to only a transmitter, a computer, and enough control to keep pointing home. A human spacecraft would not have that freedom. It could not turn off the system that circulates breathable air. It could not allow the water supply to freeze. It could not abandon the heaters protecting the sleeping quarters. It could not sacrifice one inhabited module after another without eventually running out of places where the crew could survive. For a human voyage, warmth would not merely protect the mission. It would define the borders of the habitable world. Inside those borders, air would move, water would flow, and people would sleep. Outside them would be the endless night, and only a few inches of engineered material would separate the two. Imagine opening your eyes inside a spacecraft far beyond Mars. For a moment, nothing feels unusual. The air around you is warm. A small reading light glows beside the sleeping compartment. A ventilation fan turns somewhere behind the wall. Fabric straps hold your body gently in place so that you do not drift across the cabin while you sleep. The temperature is about 70 degrees Fahrenheit. Comfortable. Ordinary. Almost exactly what you might expect inside a bedroom on Earth. But only a few inches beyond the wall is an environment with no breathable air, no natural warmth, and no sound. The nearest planet may be millions of miles away. The sun may have become little more than a bright point outside the window. And surrounding the spacecraft in every direction is a vacuum through which no voice, wind, or weather can travel. The room feels safe because thousands of small processes are working together to make it feel that way. Air is moving through hidden ducts. Carbon dioxide is being removed. Moisture from every breath is being collected. Heat is being carried away from your body and transferred toward radiators outside the ship. Heaters are protecting pipes that pass through colder sections of the structure. Sensors are measuring temperatures in places you will never see. Computers are comparing those measurements with narrow limits defined years before the spacecraft left Earth. Nothing about the warmth around you is accidental. It is an engineered condition. On Earth, a room can remain livable even if many systems stop working. Turn off a fan, and natural convection still moves some air. Open a door, and the atmosphere of another room mixes with yours. If the heater fails, warmth stored in the walls, furniture, ground, and surrounding air may keep the space comfortable for some time. Morning eventually arrives. Sunlight returns. Weather changes. A warmer day may follow a colder night. Deep space offers none of these corrections. There is no natural cycle waiting to restore balance. No sunrise powerful enough to rescue a cold habitat beyond the outer planets. No surrounding atmosphere to absorb excess heat from a room that has become too warm. No ground beneath the ship storing energy from the previous day. The spacecraft must create every condition that life expects. This is especially clear in microgravity. On Earth, the air you exhale is warm. It rises and mixes with the room. Cooler air replaces it. The movement is so natural that you rarely notice it. But inside a spacecraft, warm air does not automatically rise. Cool air does not fall. Without gravity creating those currents, a pocket of exhaled carbon dioxide can remain near the face of a sleeping astronaut. Breath after breath adds more gas to the same region. Oxygen becomes less available. The person may begin experiencing headaches, confusion, or breathlessness without understanding why. This is why the gentle sound of ventilation fans is not merely background noise. It is the sound of breathable air being continuously rebuilt around the crew. Fans push oxygen-rich air toward sleeping stations. They carry carbon dioxide toward removal systems. They move warm air away from electronics. They prevent hot and cold pockets from forming in corners of the cabin. A silent spacecraft might seem peaceful. But in deep space, complete silence could be a warning. The fans must turn, pumps must vibrate, valves must open and close. The habitat remains alive through motion. Water presents another quiet challenge. It moves through the spacecraft for drinking, food preparation, cooling, hygiene, and oxygen production. Some of it travels through pipes close to the warm center of the habitat. Other sections pass near structural joints, external walls, or equipment bays that may be much colder. A pipe does not need to reach the temperature of interstellar space to become dangerous. Water freezes at a temperature familiar to anyone who has experienced winter. A small region of pipe falling below 32 degrees Fahrenheit can create a blockage. The rest of the habitat may remain perfectly comfortable. The crew may still be sleeping in warm air. Yet behind one panel, ice can begin forming in a narrow line that supports an essential system. This is one of the strange features of thermal survival in space. The spacecraft does not need to become uniformly cold. Only one important place needs to become cold enough. A battery pack may remain healthy at room temperature, but lose much of its useful capacity as it cools. A polymer seal may remain flexible for years, and then harden when its local temperature falls below its design range. A lubricant inside a mechanical joint may thicken until the mechanism can no longer move. A computer that operates safely while powered on may cool too far when shut down to save electricity, making it difficult or impossible to restart. Every system lives inside its own thermal window. The crew lives inside one as well. The human body can tolerate changes in cabin temperature, but not without limits. Too cold, and the body consumes more energy to maintain its core temperature. Sleep becomes difficult. Hands lose dexterity. Tasks take longer. Too warm, and the body begins sweating. Humidity rises. Water vapor enters the air and must be removed by the life support system. In microgravity, sweat does not drip downward. It remains on the skin or forms floating droplets. The same sealed environment that keeps the vacuum out must also process everything the crew releases into it. Heat, moisture, carbon dioxide, odors, microorganisms. A human habitat is a closed conversation between bodies and machines. The crew warms the air. The air warms the equipment. The equipment transfers heat to coolant. The coolant carries it toward the radiators. The radiators release it into space. At the same time, heaters return warmth to places that are losing too much. The spacecraft is constantly moving energy in two directions: away from where it is dangerous, toward where it is needed. This balance can create an unsettling contrast. A crew member may lie beneath a thin sleeping cover, warm and comfortable, while a nearby section of the outer hull faces temperatures hundreds of degrees lower. The wall between them is not thick like the stone of a fortress. Much of it may consist of lightweight metal, insulation, wiring, fluid lines, and carefully placed layers designed to control radiation. The safety does not come from distance. It comes from precision. The cold is not far away. It begins just beyond the controlled environment. It exists behind every exterior panel, around every window, beyond every airlock. Yet the crew does not feel it because the spacecraft continuously holds the boundary in place. This may be one of the most remarkable things about a human voyage through deep space. The astronauts are not simply traveling inside a vehicle. They are living inside a small manufactured world. A world with its own atmosphere, its own water cycle, its own artificial weather, its own carefully regulated seasons that never change. There is no winter unless a system fails. No summer unless heat accumulates. No wind except the air moved by fans. No rain except the condensation collected from breath and sweat. The habitat is Earth reduced to machinery. And every hour it continues operating, it recreates a tiny piece of the planet from which the crew came. Perhaps this is why the ordinary sounds inside a spacecraft would become so meaningful on a long journey. The steady fan above a sleeping station, the faint click of a thermostat, the distant vibration of a pump, the soft rush of air through a vent. These sounds might fade into the background after weeks or months, but each one would be evidence that the artificial world remained alive. Outside, nothing changes. The stars remain distant. The vacuum remains silent. The sun continues shrinking behind the ship. Inside, the cabin stays warm. Until one small part of the system fails to respond. A heater does not activate. A pipe begins cooling. A valve becomes stiff. At first, the room still feels normal. The crew continues sleeping. But somewhere behind the walls, the boundary between the warm world inside and the endless night outside has begun to move. Somewhere behind the wall of the spacecraft, a heater fails. It is a small device, a narrow strip bonded to the outside of a propellant line, designed to switch on whenever the temperature falls too low. It draws only a few watts. On Earth, that amount of power would seem insignificant. It might be less than the energy used by a dim lamp. But here, far from the sun, those few watts protect a line carrying the fluid that allows the spacecraft to turn. The heater does not explode. It does not produce smoke. No warning light immediately flashes across the control panel. A sensor simply stops sending the correct command. The heater remains off. At first, almost nothing happens. The metal pipe still contains stored warmth. Nearby equipment continues radiating a little heat into the structure. The propellant remains liquid. Inside the cabin, the temperature is unchanged. The crew continues working. A fan turns, a screen glows. Someone fastens a meal packet to a table. The spacecraft appears perfectly healthy. But the line is cooling. Heat leaves the metal through its connection to colder structural panels. Some escapes as infrared radiation toward the dark side of the vehicle. There is no surrounding air to slow or soften the change. Hour by hour, the temperature falls. Eventually, one small region of propellant reaches its freezing point. The process begins along the coldest inner surface of the pipe. A thin layer becomes solid. Then another. The frozen section grows inward until it forms a plug. The rest of the propulsion system remains warm enough. Most of the propellant is still liquid. Only a few inches of one narrow line have frozen. But that is enough. Later, the spacecraft's computer sends a routine command to fire the connected thruster. The valve opens. Nothing happens. The thruster does not respond. The computer waits for confirmation, detects the missing force, and tries again. Still nothing. The failure is small, but a spacecraft depends on precise orientation. Its antenna must face Earth. Its solar sensors must know where the sun is. Its instruments must point toward their targets. And its radiators must face regions of the sky where they can release heat efficiently. The guidance system activates a backup set of thrusters. The spacecraft begins turning again. The correction works. The antenna remains aligned. The crew may never notice the change, but the backup thrusters are mounted in a different location. They push the spacecraft with a slightly different balance of forces. The final orientation is only a fraction of a degree away from the ideal attitude. For navigation, the difference is acceptable. For thermal control, it may not be. One edge of a radiator that had been facing deep darkness now sees a thin slice of the sun. The sunlight is weak at this distance, but the radiator was designed to emit heat, not absorb it. Its surface begins collecting energy. Its ability to cool the spacecraft falls slightly. Again, nothing dramatic happens. The temperature inside the habitat does not suddenly rise. The change begins as a number on a screen. Coolant returning from the radiator is warmer than expected. The thermal control computer increases the speed of a pump. More coolant circulates through the loop. The system is compensating exactly as it was designed to do. But the faster pump requires additional electricity, only a small amount. A few more watts. The spacecraft's power system responds by reducing energy available elsewhere. A heater protecting a battery pack cycles on less frequently. Another heater around a water line remains off for several extra minutes. The changes are within normal limits. For now, the thermal system is built with margins. It can tolerate temporary imbalances. It can borrow power from one location and use it in another. But deep space turns every margin into a limited resource. The battery pack begins to cool. As its temperature falls, its ability to store and deliver energy decreases. This means the spacecraft has slightly less reserve power available during periods of high demand. To compensate, the computer postpones a scientific observation. An instrument that would normally be active remains switched off. That saves electricity. But the inactive instrument no longer produces waste heat. The compartment around it cools. A nearby electronics unit now requires more heater power to remain above its minimum temperature. The power that was saved in one place is quietly demanded in another. This is how a thermal cascade grows. Not through one enormous failure, through many small corrections that change the conditions surrounding other systems. The radiator receives a little too much sunlight. The pump uses a little more power. A battery receives a little less heat. An instrument stays off. A compartment becomes colder. Another heater runs longer. Each event makes sense on its own. Together, they begin changing the entire thermal balance of the ship. Several hours later, the battery pack has lost part of its usable capacity. The spacecraft can still operate, but the reserve that protects it during emergencies is smaller. At nearly the same time, a water pipe passing through a colder structural joint approaches the freezing point. The line supplies coolant to an equipment bay. A thin ring of ice forms inside the pipe. The flow becomes restricted. Less warm fluid reaches the equipment beyond the blockage. Those components begin cooling. But upstream from the blockage, the coolant cannot circulate normally. Heat from active electronics begins accumulating. One side of the system becomes too cold. The other becomes too warm. The spacecraft is now freezing and overheating at the same time. This sounds impossible only because we imagine temperature as something that fills an entire place evenly. But in space, heat does not spread unless a path has been created for it. A warm component can sit close to a frozen pipe without being able to help it. A radiator can face deep cold while the cabin behind it grows hotter. A battery can lose capacity from low temperature while a computer a few feet away approaches its maximum operating limit. The spacecraft is not one thermal object. It is a network of small environments connected by pipes, wires, metal supports, insulation, and fluid loops. When one connection fails, those environments begin drifting apart. The crew finally receives the first clear warning. The coolant temperature in one equipment bay has risen beyond its expected range. A second alarm reports low flow in a water loop. Another indicates reduced battery performance. Each message appears to describe a different problem. A cooling problem. A plumbing problem. A power problem. But beneath them is a single thermal disturbance that began with a heater strip attached to a propellant line. The crew starts troubleshooting. They power down non-essential computers to reduce the heat load. Cabin lighting dims. A scientific instrument is placed into a safe mode. The lower electrical demand helps the radiators catch up. But the powered-down equipment begins cooling. If it becomes too cold, restarting it later may be difficult. The crew must decide which systems can safely be allowed to cool and which must remain active. Every choice moves heat and power through the vehicle in a different way. A human spacecraft cannot simply shut down indefinitely. Air must continue circulating. Carbon dioxide must continue being removed. Water must remain liquid. Communication must be maintained. The crew must stay warm enough to think clearly and work safely. Even sleep depends on machines that consume power and generate heat. The ship has entered a narrowing corridor. Too much activity and the interior overheats. Too little activity and critical equipment begins freezing. The failed propulsion line introduces another danger. Frozen propellant expands and contracts differently from the metal surrounding it. When heaters eventually restore warmth to the pipe, the solid plug begins melting. The fluid and metal warm at different rates. Stress concentrates around joints and fittings. A connection that survived the first freeze may weaken during the thaw. If the line freezes again, microscopic cracks can grow. Thermal damage is often cumulative. A component may survive one extreme cycle, and another, then fail during an event that appears no worse than those before it. Materials remember. Metal expands and contracts. Seals harden and soften. Adhesives lose strength. Solder joints develop tiny fractures. Electrical resistance changes. The spacecraft ages through temperature. The original heater failure may eventually be isolated. The propellant line can perhaps be warmed. The orientation can be corrected. The radiator can once again face the dark sky. But the spacecraft may not return completely to the condition it had before. The battery has been stressed. A pipe has partially frozen. A fitting may have weakened. Equipment has operated outside its preferred temperature range. The cascade leaves scars. This is what makes the cold of deep space so dangerous. It does not need to freeze the entire ship. It only needs to move one important component a few degrees beyond the range in which it can function. Once that happens, the spacecraft's own interconnected systems can carry the disturbance farther. Cold becomes a guidance problem. Guidance becomes a radiator problem. Cooling becomes a power problem. Power becomes a heating problem. And the ship slowly loses the ability to protect the very systems it needs to recover. There is no blizzard outside. No wall of ice striking the hull. No visible enemy. Only a few watts missing from one quiet corner of the spacecraft. And in the deep darkness between worlds, that can be enough to place an entire artificial world at risk. The spacecraft continues outward. Behind it, the sun has become only one bright point among many. Ahead, the darkness does not appear colder than the darkness already surrounding the ship. There is no visible boundary between the outer solar system and the space between the stars. No curtain is crossed. No alarm announces that the vessel has entered a new climate. The stars remain distant. The cabin remains warm. And yet, the sources of natural heat are becoming fewer. To understand how cold the universe can become, we do not always need to travel beyond the solar system. Some of the coldest places nearby exist on the moon. Near the lunar poles, deep craters hide regions that sunlight may not have reached for billions of years. The moon's axis is tilted only slightly, so the sun remains close to the horizon near the poles. The floors of certain craters lie behind walls tall enough to block direct sunlight through every lunar season. These places are known as permanently shadowed regions. They are not merely dark during the lunar night. They are always dark. No sunrise crosses the crater floor. No atmosphere scatters light into the shadows. No warm wind descends from the illuminated rim. The ground receives only faint reflected light and weak infrared radiation from the surrounding terrain. Over immense spans of time, the surface has released nearly all the energy it once stored. Some of these shadows fall to temperatures around 25 to 40 Kelvin. Cold enough to preserve water ice and other volatile materials for geological ages. A molecule that enters one of these regions may remain trapped there, frozen into the soil, while the sunlit landscape only a short distance away becomes hot enough to damage unprotected equipment. This reveals something strange about cosmic cold. The coldest places are not always the places farthest from a star. Sometimes they are places that simply cannot see it. A crater wall may create a colder environment than millions of miles of additional distance. A shadow can become a world of its own. Farther from the sun, the surfaces of distant objects cool more completely. Pluto receives only a faint trace of the sunlight that warms Earth. Its surface is covered with ices made not only from water, but from nitrogen, methane, and carbon monoxide, materials that would exist as gases in familiar terrestrial conditions. Beyond Pluto, smaller bodies move through the Kuiper Belt and the more distant regions of the solar system. Some have not felt strong sunlight since the planets were young. They preserve ancient materials from the time when the sun itself was forming. But even there, complete cold does not exist. Radioactive elements inside a world may continue producing heat. Impacts can briefly warm the surface. Distant sunlight still arrives. And every object is surrounded by the faint radiation left behind by the early universe. The cosmic microwave background remains everywhere. It passes through the solar system. It fills the spaces between stars. It crosses the enormous voids between galaxies. No object can hide from it completely. Yet the universe contains rare environments that can become even colder than this ancient background. One of the most famous is the Boomerang Nebula. It surrounds a dying star whose outer layers are being expelled into space at extraordinary speed. As the gas expands, it cools. This is the same basic reason compressed gas becomes colder when it is allowed to expand rapidly, though the scale of the nebula is vastly greater. The outflow has cooled portions of the surrounding gas to approximately 1 Kelvin, colder than the cosmic microwave background. For a time, the expanding gas absorbs some of the microwave radiation passing through it, creating one of the coldest natural environments known. The Boomerang Nebula is not cold because it has been sitting quietly in darkness. It is cold because matter is moving outward so quickly that its internal energy is being spread across an expanding volume. Even the background glow of the universe can appear warm by comparison. But this extraordinary cold will not last forever. The nebula will continue evolving. Its gas will mix with the surrounding interstellar medium. Radiation from nearby stars and the cosmic background will gradually alter its thermal state. Like nearly every extreme condition in the universe, it is temporary. This is another lesson hidden inside cosmic temperature. Cold is not simply a location. It is a process. A world cools because it emits more energy than it absorbs. A cloud cools because it expands. A spacecraft cools because its heaters weaken. The universe cools because it grows larger. The cosmic microwave background was once much hotter than it is today. In the early universe, space was filled with radiation intense enough to prevent atoms from forming. As expansion continued, the radiation stretched into longer wavelengths and lost energy. The background temperature fell. It is still falling. Very slowly. The change is far too small to notice across a human lifetime, but over cosmic time, the universe continues moving toward a colder state. We live during an era of light. Stars fill galaxies. Gas clouds collapse. New suns are born. Planets receive warmth. Chemical reactions unfold. Life can use differences in energy to grow, move, remember, and think. The night sky may look dark, but the universe around us contains countless fires. Every star is a temporary island of concentrated energy. Our sun is one of them. It has burned for billions of years and will continue shining for billions more. But stars do not last forever. They consume the fuel available in their cores. Massive stars burn brightly and die quickly. Smaller stars survive much longer. The smallest red dwarfs may continue shining for trillions of years, far beyond the current age of the universe. For an unimaginably long time, these dim stars may become the final dependable sources of starlight. Galaxies will gradually change. The gas available for new stars will be consumed, heated, or scattered. Star formation will slow. The bright blue stars that illuminate young galaxies will disappear. More of the remaining light will come from small, cool stars that use their fuel with extraordinary patience. Eventually, even they will fade. The universe will not become dark in a single moment. Like Voyager losing power, it will surrender its lights one by one. A star ends, then another. A galaxy that once contained clouds glowing with new formation becomes filled mostly with stellar remnants. White dwarfs slowly release their stored heat. Neutron stars cool. Planets drift through increasingly dark systems. Some worlds remain bound to dead stars. Others may be thrown into interstellar space through gravitational encounters, becoming rogue planets with no sunrise at all. Such a planet may still possess internal heat. Radioactive decay may warm its interior. A thick atmosphere or deep ocean beneath ice could hold that energy for astonishing periods. Even without a star, the world might not become completely frozen inside. Once again, the surface temperature would not tell the whole story. Warmth could survive beneath darkness. But every source is finite. Radioactive elements decay. Stored heat escapes. Differences in temperature gradually become smaller. As long as one region is warmer than another, energy can flow. Machines can operate. Chemistry can continue. Life, at least in forms we understand, can make use of that difference. But when temperatures become nearly equal everywhere, there is less available energy to perform useful work. This is the deeper meaning behind the distant thermal future of the universe. It is not merely that everything becomes cold. It is that the contrasts begin to disappear. No hot star above a cold planet. No warm interior beneath an icy surface. No reactor producing power against the darkness. No radiator with a colder sky into which it can release heat. Temperature difference is opportunity. It allows energy to move, and energy in motion allows change. The universe may continue existing for timescales that make the age of the stars appear brief. Black holes may remain after ordinary starlight has vanished. They, too, are not completely eternal. Through an extraordinarily slow quantum process, they are expected to lose energy and eventually evaporate. For the largest black holes, this would require lengths of time so vast that ordinary numbers become almost meaningless. Long after planets have cooled and stars have faded, the final black holes may release their remaining energy into an almost empty universe. Then even those last concentrated reservoirs will be gone. What remains would be thinly distributed particles and radiation moving through an ever-expanding darkness. Not a universe suddenly frozen. A universe with almost no usable warmth left to gather. The deep space vessel traveling through our story is a much smaller version of this same struggle. Inside the ship, energy is concentrated. The cabin is warmer than the void. The generator is warmer than the cabin. The crew's bodies are warmer than the air surrounding them. Heat flows through designed pathways because differences still exist. The spacecraft is alive, in a physical sense, because energy is still moving. Its pumps turn. Its fans circulate air. Its computers organize electrical signals. Its radiators release infrared photons into the dark. The ship maintains a small region of order against a universe that naturally allows energy to spread outward. But it cannot do this forever. The fuel supply is finite. The generator ages. The materials weaken. The difference between the warm interior and the cold outside can be maintained only as long as the machinery continues working. This does not make the warmth inside less meaningful. It makes it more remarkable. The universe is filled with cold regions, shadows untouched by sunlight, worlds beyond the reach of meaningful solar warmth, expanding clouds colder than the ancient radiation around them, and a distant future in which the stars themselves no longer shine. Yet here, inside one small vessel, air remains warm enough to breathe. Water still flows. A sleeping person releases heat into the cabin. A tiny heater protects a pipe. A generator produces another watt. Against the scale of the universe, these things are almost impossibly small. But for the people inside, they are everything. And as the spacecraft drifts beyond the last familiar warmth, the most important question is no longer how cold the darkness outside can become. It is how long the small world inside can continue carrying its warmth forward. Return now to the small room inside the spacecraft. The lights have been dimmed. The crew is resting. Beyond the windows, Stars remain scattered across the darkness, so distant that they appear almost motionless. There is no visible wind outside. No snow. No frost forming across the glass. Only the silent vacuum, extending in every direction. Inside the cabin, the air remains warm. A fan turns slowly behind a panel. Coolant moves through a hidden pipe. A thermostat measures the temperature of a fuel line and quietly activates a heater for a few moments. Somewhere deeper in the ship, a generator releases another small amount of energy. A computer processes a command. A radiator sends invisible infrared photons into space. Nothing about these events seems dramatic, but together, they are keeping an entire world alive. This is what the cold of deep space truly means. It is not a storm waiting outside the hull. It is not an ocean of freezing air pressing against the ship. It is not a force that reaches inward and turns everything to ice in an instant. Deep space is dangerous because it offers almost nothing. No atmosphere to carry warmth. No wind to distribute it. No ocean to store it. No nearby ground to release heat after sunset. And eventually, no star close enough to provide the energy a spacecraft needs. The universe does not actively steal the warmth inside the ship. The ship gives that warmth away on its own. Every warm surface releases radiation. Every operating machine produces heat. Every living body adds energy to the cabin. The spacecraft must decide where that energy goes. It must hold warmth near batteries, pipes, seals, and sleeping crew members. It must move excess heat away from computers and life support equipment. It must protect some parts from the sun while exposing other parts to the dark. It must create pathways where nature provides none. On Earth, we rarely notice how much thermal work the planet performs for us. The atmosphere moves heat from place to place. Oceans absorb energy during warm periods and release it during cooler ones. Clouds reflect sunlight. Wind mixes the air. The ground stores the warmth of the day. Night is followed by morning. Winter is followed by spring. Even when conditions become harsh, the environment continues changing. A cold night does not last forever. A storm eventually passes. The sun rises again. Deep space makes no such promise. A spacecraft cannot wait for warmer weather. It cannot open a window when the cabin overheats. It cannot build a fire from materials found outside. It cannot depend on a new day bringing more energy. Everything required for survival must already be on board. Every heater, every pump, every radiator, every spare part, every source of power. The ship is a small, artificial world carrying its own climate through a place without one. And that may be the most important way to understand human travel beyond Earth. We are not simply sending machines through space. We are carrying pieces of our planet with us. A breathable atmosphere, liquid water, comfortable temperatures, a cycle of air and moisture. The chemical conditions required by living cells. Inside the spacecraft, Earth continues in miniature. The crew exhales carbon dioxide. Machines remove it. Water vapor leaves their skin. The habitat collects it. Their bodies produce heat. The thermal system moves that heat through the ship and releases it into the universe. A tiny part of Earth's energy becomes infrared light, traveling away into the darkness. The photons do not know they once came from a human body. They do not know they passed through a warm cabin. They simply continue outward. Perhaps some will cross the solar system. Perhaps they will pass near distant stars. Perhaps they will travel for millions of years without touching anything at all. Behind them, the spacecraft continues moving. Its engines may be silent. Its direction may change only occasionally. Its journey may last months, years, or decades. But as long as the fans continue turning, the water continues flowing, and the generators continue producing power, the small world inside remains alive. That life is not protected by the kindness of the universe. It is protected by understanding. By knowing how heat moves. By knowing that cold is not simply a temperature, but a relationship between energy gained and energy lost. By knowing that a surface in sunlight can overheat, while another surface a few feet away freezes. By knowing that a single failed heater can affect a valve, a thruster, a radiator, a battery, and eventually an entire habitat. And by knowing that far from the sun, 1 watt can become the difference between a machine that functions and one that falls silent. This is why the cold of deep space is worse than you think. Not because it freezes a human body instantly. It does not. Not because every object in space shares the same temperature. It does not. And not because darkness itself is reaching toward the ship. The danger is quieter. The cold waits beyond every controlled boundary. It appears wherever power is lost, wherever heat can no longer be moved. Wherever a pipe, battery, seal, or circuit drifts beyond the narrow range in which it was designed to survive, it advances not in miles, but in degrees. Not through dramatic impact, but through declining margins. A few watts less. A heater remaining off for too long. A radiator facing the wrong direction. A fluid becoming slightly more viscous. A seal becoming slightly less flexible. A battery holding slightly less charge. The spacecraft does not need to freeze completely. It only needs to lose control of where its warmth is allowed to go. And yet, there is another way to see this story. The darkness outside may be vast. The universe may be cooling. The stars may not burn forever. But for now, warmth still exists. Stars still shine. Planets still orbit them. Energy still moves through oceans, atmospheres, machines, and living bodies. And a species born beneath one ordinary star has learned how to carry that energy beyond the world where it began. A spacecraft in deep space is like a small candle moving through an endless night. The flame is protected. The fuel is limited. The darkness around it is immeasurably larger. But the candle is still burning. Inside the vessel, someone is sleeping. Their breathing is slow. Warm air moves gently past their face. The ventilation system carries each breath away and returns fresh oxygen. A heater clicks off after protecting a pipe from the cold. A pump reduces its speed. The cabin settles into its quiet nighttime rhythm. Outside, the sun is far behind. Its light still crosses the distance, but its warmth has faded. Ahead, the stars remain impossibly remote. The spacecraft drifts between them, carrying air, water, memory, and heat. Carrying a small portion of Earth into a place where Earth was never meant to exist. And perhaps that is the final truth, hidden inside the cold of deep space. Warmth is not something we can take for granted. It is something temporary, something precious, something that must be protected, moved, shared, and renewed. Every warm breath inside a spacecraft is proof that the darkness has not won. Every functioning circuit is a small act of resistance. Every drop of liquid water is a triumph of balance. And every sleeping traveler is surrounded by the warmth of a world carried far from home. The ship continues onward. The fans continue turning. The final lights grow dim. And within the vast, patient cold, the little artificial world remains warm.